Okay, why don't we start here? This will be our last session. And as you'll see from your notes, there's a whole lot more in the notes than I've had time to get through, so I'm just trying to grab certain key topics. What I want to, so we've talked about just general disturbance propagation. I hope I've given you some background on just the fundamental differences between acoustic and vortical and entropy modes, all of which are coexisting in reacting flows, and how they interact with each other plays a critical role in many problems, whether it's jet noise, whether it's shock waves propagating through temperature gradients, whether it's jet noise problems, whether it's combustion instability. So the last topic that I want to leave you with here is understanding the sensitivity of flames to disturbances, and specifically the sensitivity of flames to harmonic excitation, right? So as we've talked about, combustion instabilities, they manifest themselves as very narrow band oscillations. So here's an example spectra, very, very narrow band, as opposed to what you would see in high Reynolds number flows where you have Navier-Stokes turbulence, where you have very broad band velocity spectrum. When you place those disturbances inside of a resonator, they get filtered. And so the turbulent flame problem, in other words, how do flames respond to convecting vortical fluctuations? The turbulent fluctuations are basically vortical disturbances. Has many very, very different features from the combustion instability problem because of the space-time coherence of the disturbances. In the turbulent problem, you're looking at how flames respond to convecting disturbances with a broad range of space and time scales with a certain amount of memory, a certain space-time correlation. Whereas the combustion instability problem, what you're looking at is similarly how do flames respond to disturbances. Either those could be acoustic disturbances or vortical disturbances, but the key difference being is that the space-time coherency, they're very, very space-time coherent. That the coherence time scales can be very, very long. And so it's sort of like understanding the difference between a laser, where a laser has very coherent light output versus just these lights in this room. Just very, very different characteristics. So this is what we want to focus on here. And the basic problem that we're interested in is again, we have these heat release oscillations. They're exciting the flame. They're part of this feedback loop where we have heat release fluctuations exciting acoustics. These acoustic fluctuations both directly excite the flame. They also excite fluid mechanic instabilities, which excite the flame. In this feedback loop, the amount of time it takes to go around one loop is one period of oscillations. And so the question that I want to talk about here is, how do we relate these heat release fluctuations? In other words, what's the transfer function? If you think about your controls classes, what's the transfer function? What's the input-output relationship? If I disturb a flame with an amplitude a velocity disturbance of amplitude x, what is the heat release fluctuation? What is the amplitude and what is the phase delay of that heat release response? So just to give you a feel for some typical data, these are what measurements look, a very typical measurement of what a flame transfer, this would be a flame describing function actually, might look like. This is the spatially integrated heat release. So if we take the heat release from the flame as estimated by the chemiluminescence off the flame, and we don't look at what it's doing at a given one point or another, we just say, let me just integrate it. And this would be data showing the sensitivity of the heat release to velocity disturbances. So the x-axis here, U prime denotes the magnitude of velocity fluctuations, U naught denotes the mean, Q prime denotes the magnitude of heat release fluctuations, Q naught would be the mean. So in other words, and this is data. So what it's showing you is that when we excite the flow such that the velocity is oscillating at a value that's 20% of the mean. So if the mean velocity is 50 meters per second, it's oscillating at some frequency between 40 and 60 meters per second, harmonically. And then we look at what the magnitude of the oscillations are of the heat release. You can see it's oscillating at 30%. So in other words, the 20% oscillation in velocity is giving you a heat release oscillation of 30% around its mean value. A value of 0.1 would be 0.15. What you can also see is there's this range where this plot is linear, right? So the flame is behaving as a linear input-output plant. Again, if we think about controls, a controls description of it, we have some input to the plant, we have the output, and it's acting linearly. So what that means is if I double the amplitude of excitation, I double the amplitude of the response. If I triple the amplitude of excitation, I triple the amplitude of the response. It's a straight line. But you can also see there's the curve bends over, and we get this, in fact, we get a pretty hard saturation. So what that means is that the magnitude of the heat release fluctuations at 40% velocity fluctuations is pretty much the same as it is at 60%. All right? And so what I can do is actually the slope of this curve right here is basically the gain, right? Q prime over Q naught divided by U prime over U naught. That's the gain of the transfer function. And I can plot that. This is data. It turns out this is a model. This would be the gain of the transfer function. You can see that the gain is 1.5 here, so it would actually be 1.5. And I'm plotting, in this case, this would be modeled results for a flame transfer function as a function of a dimensionless frequency, what we're calling a Struhal number, which in this case turns out to be the frequency times the flame length divided by the flow velocity. And you can see that the gain has a frequency dependence. So what I want to talk about today, now for the rest of this time, is what factors affect the slope of this curve? What gives it that gain relationship? And other questions I want us to think about is, why is this curve saturating? Why is the flame saturating? Why is it saturating at this amplitude? Why isn't it saturating at 20% of the mean? Why doesn't it keep right on going and saturating at 100% of the mean? And these are very, very important questions from a combustion instability standpoint, because this saturating behavior has a really important influence on what the amplitude of the instability turns out to be. You'll have to take my word for it. I didn't have time. I won't have time to explain that. But this, it turns out that the slope of these curves has a really important influence on the conditions under which instabilities happen. And this saturation has important influences on what the resultant amplitude are if you are unstable. And so the difference between a 1 psi instability, a 0.1 psi instability, and a 10 psi instability, as you can imagine, if it's 0.1 psi, well, you may not work in psi units. So if the magnitude of the pressure fluctuations are 1/10,000th of the mean pressure, it may be an instability. It might be something interesting to study on a Saturday afternoon, but it may not have any real impact on the performance or the life of a component. Whereas if the fluctuations are 10 or 50% of the mean, the system might not work at all. You may not be able to operate. And and so understanding what's happening in those two circumstances is very important. Okay, so what I want to do for the rest of this time here is kind of give you a feel and give you some language to understand quantitatively what's controlling this. And I'm going to be going back and forth between data and modeling results. So for the modeling results, we're going to be looking at both premixed and non-premixed flames, and we're going to be using the flamelet formulation. All right? So the flamelet formulation, in essence, what we're going to say is that all the heat release is occurring over a length scale that's really, really small relative to the other length scales that's happening. And so the essence of what I'm going to be trying to do is I'm going to be collapsing all the interesting chemistry, for all that you learned from the faculty earlier this week, all that interesting chemistry, we're going to collapse that into a discontinuity, in essence, and I want to track the space-time features of that discontinuity, whether it's a premixed flame or a non-premixed flame. I want to track where the flame is, and I want to track what the heat release rate per unit area of the flame is. Okay? Now, certainly, that's not to say that the kinetics doesn't influence the problem, because, like for instance, for a premixed flame, the flame speed, SL, is controlled by the kinetics, and where the flame is very much influenced by SL. But we're going to work within what's called the G and the Z equation framework. So I'll start with the Z equation. And by Z-equation, I'm just referring to the mixed diffraction equation, which you talked about earlier this week. And if I'm going to jump over the key steps here, but if you remember that if you assume that the Lewis number, actually we don't assume Lewis number is 1, this is not quite correct. If we assume that all of the species have the same diffusivity, you can write a sourceless equation, right? So here, for example, would be a species equation for fuel or products. But if the diffusivities are the same, I can multiply these different species equations by stoichiometric coefficients and get a sourceless equation, like I've written here, all right, which would be, and so you can write, and this is a conserved scalar, the whole conserved scalar approach. And so the, if Z, I'm going to call Z the mixture fraction, I can write an equation like this for the mixture fraction. Remember, the mixture fraction is just the mass of particles originating in the fuel jet divided by the total mass. And it's a sourceless equation if the diffusivities are the same. And so this is a nice equation because what I can do is if I can solve the Z equation, and particularly here I've expanded out the substantial derivative. If I'm interested in a problem like what is the sensitivity of a premixed flame to velocity disturbances, I can take a problem where I modulate U, and I can modulate it harmonically, and then I can solve for the space-time characteristics of the Z field, which will give me the Z field everywhere. Now, let me back up a slide. Within the flamelet approximation, all the heat release is happening at the Z-Stokes surface, right, where the mixture fraction is equal to its stoichiometric value. So what I can do then is I have this equation for the entire Z field. Z is a field, mixture fraction field, but I'm particularly interested in the isocontour where Z is equal to Z-Stoke, all right? So if I can track Z, if I can extract the Z-Stokes surface, that will then give me the space-time characteristics of where the flame is. And as I'll show you, the flame is wrinkling and flapping around, and we can model this and we can see it in data. In the same way, the gradient of the mixture fraction normal to the Z-Stokes surface tells us about the mass flux into the flame, and that tells us something about the heat release. All right? So I'm interested in the value of the Z-Stokes surface, both the position, the space-time position. I'm also interested in the gradient of the Z-Stokes field because that tells me heat release. That's for a non-premixed flame. Now, for a premixed flame, I can similarly write a flamelet equation. How many of you are familiar with the G-equation? Okay, so many of you are. So the G-equation is a very useful equation for the space-time dynamics of a premixed flame sheet. And I'll just quickly go over it. The basic idea is let's assume that I have a field, and I'm going to call that field G. G is a field, and it's a function of space, and it's a function of time. All right? And G is going to smoothly vary between a value that's less than 0 to a value that's greater than 0. And I'm going to define G such that where G is equal to 0, that will be a surface, and that will correspond to the flame sheet. And if I take a Lagrangian coordinate system, so if I'm always riding on the flame, then dg by dt will equal 0. And then if I expand that out, I can write dg by dt plus vf dot grad g. Vf denotes the flame velocity, not the flame speed, but the velocity of the flame sheet. And then I referred to this relationship yesterday. I can relate the velocity of the flame sheet to the gas velocity and the displacement speed. Right? Those three are related. So I can replace that by the velocity field and the flame speed. I also, remember the flame is propagating normal to itself. So what this equation is basically saying is what the velocity of the flame sheet is going to equal the gas velocity. So the gas velocity is going to be pushing the flame around. But the flame is also going to be moving normal to itself. Right? So the flame is resisting that motion in SD as a scalar, but N as a vector. And then I can just use this relationship for the normal of a field. It's grad G over mag grad G. So if I substitute these two expressions in, I end up with an equation like this, or written over here. This is what's called the G equation. This is an equation that describes the space-time dynamics of the G field. All right? And again, what I can do is if I can solve this equation, figure out where G is equal to 0, that gives me the space-time description of the flame position. All right, I'm going through this stuff kind of quickly, but it's presented in more detail in the book, and there's other resources for it. The main reason we're going to be solving these equations, and I want you to know that I didn't just pull them out of the air. Now, this, in general, G is a field. It has a value, like I said, it has a value less than 0 in the reactance, greater than 0. It would be nice if I could just write an explicit equation for the flame position itself. And this is what if the flame position is a single-valued function of some variable, it turns out that you can. So in other words, let's look at this geometry. If this is the instantaneous location of the flame sheet, so all the chemistry is collapsed within this sheet, and I'm parameterizing all this diffusion and differential diffusion and kinetics and Lewis number effects, those basically, within this formulation, they collapse into this one parameter flame speed. So let's just suppose that I have a coordinate system where this is x, this is y. The instantaneous flame position I will define this variable zeta, which is a function of y and t. If it's a single-valued function, then I can define this value for g. I'll say g is a field, and by defining it this way, x minus zeta of y and t is equal to 0, you can see that when I'm at the flame, g will equal 0. And if I'm in the reactance, G is going to be less than 0. If I'm in the products, it's greater than 0. If I substitute this equation in to here, I actually end up with an explicit expression for the space-time dynamics of the flame position. All right? So this, and you can see it has a convection operator on the left-hand side, and it's got this nasty nonlinearity. And this is due to flame propagation. The fact that premixed flames propagate normal to themselves gives them this geometric nonlinearity, this square root of 1 plus the slope of the flame position squared nonlinearity multiplied by the flame speed. But what's nice about this is that for premixed flames, I can actually write an explicit equation. This equation tells me the space-time dynamics of where the flame is. So again, if I want to know if I have an oscillatory velocity field, maybe it's a vortex. If I have a convecting vortex, the shear layer is rolling up, it's convecting downstream, I'll have some space-time velocity field distribution. I can substitute that in here into my velocity field, and I can solve this partial differential equation for the flame position. It will tell me how the flame is responding, which is really powerful. Or maybe I have a fuel-air ratio disturbance, which is exciting the flame. Suppose the fuel-air ratio is convecting through, and it's causing the flame speed to oscillate. Well, again, I can impose the space-time distribution of the oscillatory flame speed, solve this thing for the flame position, and again, I can calculate what's doing. So it's pretty powerful. Let me, I'm just going to jump over a few more, I have a few more details on it here. And let me now just start talking about, with that as kind of a quick overview of the governing equations, now let me specifically talk about premixed flame dynamics. All right? So I want to start by just, for those of you who aren't used to thinking about how do flames respond to harmonic disturbances, I want to help try to build some insight by just showing you some images. All right, so here's data. These are me scattering images. Flow is going bottom to top, and the flames are stabilized by a triangular Bluff body. Okay, so and what if the light region is reactants, the dark region is products. The interface between them is the instantaneous position of the flame. And so here's a movie. So the flow is getting perturbed. I'll tell you that I have an acoustic wave that's bouncing around up and down. And what that acoustic wave is also doing is it's exciting the shear layer, and you're exciting this convecting train of vortices, which is convecting downstream. And you can see the flame wrinkling as it's as these disturbances are pushing the flame around. So this would be for a relatively small amplitude of disturbance. This would be a little bit larger, so you can see the flame ring. This is twice the amplitude of that. So you can see these wrinkles are bigger. You can, in some cases, see the whole vortex starting to roll the flame up. This would be the largest, a 10% fluctuation. And you can clearly evident that you have larger amplitude velocity fluctuations, but also you can get some insight into saturation as well. Obviously, the flame is not wrinkling 10 times more in that picture than it is in this picture. So you're getting some saturation phenomenon. It's also pretty evident that the source of the wrinkles is a vortex, right? It's pretty obvious here that although you have an acoustic wave which is moving up and down, what's actually wrinkling the flame, this picture is showing, is a vortex, just as manifested by the flame getting rolled up by that vortex. So what this is showing is that although the acoustic field has a fluctuating velocity component, the way that its effect is most manifested in the flame is by modulating the strength of this separating shear layer and causing these vortices to pair in such a way that they're convecting downstream at a frequency equal to the forcing frequency. Okay. All right. Well, that's a relatively simple configuration. Yes, sir. The same velocity as the flow velocity? Okay, so in general, the convection speed of a vortex is not the same as the flow velocity because the vortex is riding in a shear layer. The reason you have the vortex in the first place, what creates it is shear. You have the Kelvin-Helmholtz instability. And so the vortex is riding, if you think about it, I have high flow velocity here, reverse flow here. The vortex is somewhere in the middle. So, kind of a rule of thumb that people sometimes use is that the vortex convection speed is the average of the two flow velocities. That's an approximation. More generally, it's a function of frequency. So you're asking a hard question, but it's not the flow velocity. Yes?
Specific reason why both vortices are shading together?
Well, yeah, you mean why is the left and right side in phase?
Yeah.
It's because I'm exciting this situation with a plane wave, and so what's happening on this side, the excitation is exactly in phase with the excitation on that side. If I was exciting the flame with a wave going back and sideways, the phase of the excitation here and here wouldn't be the same, and you wouldn't see that.
That is in when only fluid mechanics, non-reacting flows are excited around a triangular or a cylindrical cylinder, circular cylinder. That doesn't happen. The vortices shade are one clockwise and they don't get shade in a...
So you're saying if you have an axisymmetric Bluff body in the non-reacting flow, you don't excite an axisymmetric disturbance?
Yeah, even if axisymmetric or triangular, like any circular cylinder or triangular cylinder, that doesn't matter. But if the flow is excited, is non-reacting, always the vortex is...
Yep. Yeah, no, I see what you're saying. You're saying if this was a non-reacting flow, there'd be staggered. The vortices would be staggered. Yeah, no, it's a good point. For a wake flow, there are two types of disturbances, what are called sinuous and varicose. So this would be the sinuous mode, where the response is symmetric, and the other would be the varicose mode, where it's asymmetric, which is the response you're talking about. It turns out that when you have a flame, you suppress that varicose mode, and the dominant mode is the sinuous one, which is why they're in phase here. By the way, even going to your question, even in the non-reacting flow, if you force a Bluff body hard enough with a symmetric forcing, what you will oftentimes see is right near the Bluff body, you'll see symmetric, and then those vortices will stagger because it's the asymmetric disturbances which are most amplified, and so any small imperfection in those vortices, they're almost in phase, but they're not quite, and then because that asymmetric configuration is so much more unstable than the symmetric, they'll stagger really quickly. But if you look at it in the near field, right near the Bluff body, it'll actually be symmetric. Yes?
How you are oscillating the Bluff body, or you are having speaker?
No, this is in a duct. There's a piece of pipe that goes down, and I have a speaker below it, which is forcing the thing up and down. So that was a relatively clean flow. This is I know a number of you in this room are working on swirl flows. This is a Pliff image of a swirl flow, an acoustically excited swirl flow. So what we have here is flows going left to right, and so the flow is oscillating back and forth. So this is OH planar laser-induced fluorescence. So what we have is we have this annular jet of reactants coming out, and where you see the color is where there's OH. So that means you're in the products. Where it's dark blue, you're in the reactants. The flame is sitting right at that discontinuity. And so you can kind of do, this lets you see how the flame is evolving. And so it's pretty obvious that this flame is surging in and out as it's being excited. So here, as we go from here to here, you can see, in fact, the whole flame is getting rolled up by a vortex. In fact, this is a 50 meter per second flow. So that vortex is strong enough to take a flow which comes blasting out of the nozzle at 50 meters per second. And then it actually reverses direction, so it's going backwards. So very, very strong vortex. And then as we go through the other images, you see the whole flame kind of retreating back into the nozzle. This is when the flow velocity is slowing down. In fact, it almost looks like the flame may have almost be wanting to flash back. You can just barely see that flame poking out of the nozzle there. And so you can really very, very clearly see the whole roll-up of the flame by a vortex here or by a vortex there. Okay. Here's a couple other images as well. This is a series of Bluff body stabilized flames. One of these is a movie. Yeah, there it is. Just a different set of conditions which are being acoustically excited. To your question, you can clearly see it there. And it's basically going to be nearly symmetric here, but at some point it becomes sinuous downstream there.
Again, here the velocity is more so that the Reynolds number will be more. And normally it is seen when the weight is small when the Reynolds number is large. But here it's showing opposite way. Like at 38 meters per second, the weight is seen small. But at 170,
When you say the wake is small, what are you talking about?
the weight, like unstable region was you're seeing.
You mean the width between the branches? So the key difference between these two configurations is probably the temperatures. We cross some bifurcation. Tell you what, I'd rather not delve into the differences, but there's a whole really interesting set of literature on effect of the key difference. What's happening here is the density ratio across the flame is a bifurcation parameter, and you start changing the stability of the flow. But all of these are harmonically forced up and down, and you can see the flame wrinkling magnitude. In fact, we've just drawn lines on sort of the edge of the flame. You can see these things oscillating as they go up and down. Okay, what I want to do in this next slide is if I take these edges of the flame sheet, this is just line of sight chemiluminescence, and I'm going to overlay a whole bunch of different lines, okay, at different time instances, which is what I've shown here. And these really high velocity conditions, I'm not going to look at them because there's so much turbulence in the flow that it's a little harder to see what's going on. I want to focus my attention on this lowest flow velocity one. And so what I've done is I've basically drawn a flame brush, right? So, at each instant of time there's some wrinkle that looks like this, or another instant of time it looks like that. But I'm drawing for you the magnitude of the flame brush. And so what you can see here is that very near the Bluff body, the flame is not moving around that much, right? Presumably what's happening is the flame is anchored in this shear layer, and so because it's attached there, it's just not moving around that much. And then you can see that the width of the flame sheet of the flame brush is growing as we move downstream. But then what's kind of interesting about this is that the flame brush is actually decreasing in width as we go further downstream. Now, for those of you who work in turbulent combustion, can you remind me, what do you know about how turbulent flame brushes evolve as a function of downstream distance? They increase, right? So right away, this shows us one key difference. This is a harmonically forced flame. I can tell you that if I just had the same amplitude of excitation due to broadband turbulent fluctuations, I would just see this flame brush monotonically growing in thickness. But you can see it's actually growing and then decreasing. So that's kind of interesting. Okay, now I want to be a little bit more quantitative. What I've done is I've taken that same geometry I showed you earlier, I've turned it sideways, so flow is going left to right. And here's my coordinate system, y, x. And at each x location, I have shown the flame position, and I'm calling it L. So L is a function of space and time. All right? And so, for example, this would be a plot of the flame position as a function of time, and it's oscillating harmonically. Back here is the spectrum. So in this case, I was exciting the flame from side to side at 300 hertz, and you can see that the flame is wrinkling, that the wrinkling of the flame, the flapping is at the same frequency, 300 hertz. Okay, so this is at one position, one axial position. I'm showing you where the flame is at, and so what this is doing is it's showing you that the flame is bouncing up and down. Okay, so what this shows is what the flame is doing at a single spatial location. Now let me show you what happens if I add another coordinate to the plot. So this is frequency, and now I've normalized the frequency by excitation frequency. Here's magnitude of flame wrinkling. But I've added a third dimension. This is downstream distance, x. And I've normalized x by this convective wavelength, which I talked about earlier, u0 divided by the frequency. And what I've done here is I've overlaid those spectra at a bunch of different locations. So there's a couple things that you can see. You see the narrowband peak associated with the harmonic excitation. You can also see sort of this broadband background. You see the whole broadband background sort of rising as I go downstream. This is just the flame brush, just the turbulent flame brush. The magnitude of flapping is growing as I'm going downstream. But what's interesting about this thing is what I've done is I've drawn an envelope on top of the peak, and you can see this non-monotonic spatial dependence of the magnitude of flame flapping, right? So again, let's just remind ourselves what we're looking at here. This is the spectrum, specifically the magnitude of the spectrum, so there's no phase information here. This is just telling me the magnitude of the flame flapping at a given frequency, and it's showing me how the magnitude of flame flapping is evolving with distance downstream, and it's showing you that initially the magnitude of flame flapping is growing, so it's flapping a whole lot more, whatever this would correspond to here than it is there, but then it actually comes down, so the magnitude of flapping drops. And this actually just is a quantitative way of showing you what I showed you earlier, right? This was that flame brush that I showed you here. I'm just reproducing it here, and this is showing you that same non-monotonic behavior of the magnitude of flame wrinkling. So that's one interesting observation, and as I'm going to show you later on, what's going on here is because of the space-time coherence of the forcing, we're getting interference patterns on the flame, which is something we don't see with turbulent flames. We don't see interference patterns. But when you excite a flame with a harmonic disturbance, you get these very interesting interference patterns. Okay, let me now take this plot, and I'm going to just focus on what the flame is doing at the forcing frequency. Okay, so I'm going to get rid of this axis, and I'm just going to plot this black curve as a function of downstream distance. So this is the magnitude of flame wrinkling as a function of downstream distance. Okay, and I haven't shown it yet, but this is the phase. So phase of flame wrinkling is a function of downstream distance, and I've shown it for a bunch of different conditions. And I'm normalizing downstream distance by convective wavelength. So a couple things we can see here. First of all, you can see for small x, the magnitude of flame flapping is growing as I'm going downstream. Okay? So what this is showing you is that you can kind of convince yourself if I were to extrapolate this curve back to 0, L prime would be getting close to 0. And again, this is flame attachment, that I'm exciting the flame and I'm getting an oscillatory angle of the flame at the attachment point, but the position itself isn't moving much. The angle's oscillating at the attachment point, but the position is not moving much. But as the flame moves, as you go downstream, because it's farther from the attachment point, the magnitude of that flapping is growing. It shows you that you're getting some peak in magnitude of fluctuation. Then it also shows you that it decreases in amplitude as we move further downstream. What the phase shows you is that the dependence of the phase on downstream distance is almost linear, right? These plots are almost straight lines. So somebody tell me, when you see a plot of phase versus x, that's a line, what does that mean? Yeah, it tells you that you have a traveling wave moving with constant speed, right? A constant. So if this curve was flat at 0, it would mean the whole flame is moving up and down. So when this part of the flame is going up, this part of the flame is going up. But because of this spatially varying phase, it means that when this part is going up, there's a delay between when this part's going up. And what the linear part means is that, in fact, you have that the wrinkle, it goes up here, and then it goes up here, and then it goes up here, and then it goes up here, and there's a constant velocity, that there's a fixed time delay between when this part goes up, and then this part goes up, and then this part goes up, and then this part goes up. And you can see this. So what this does is this just quantifies an observation that you could have made relatively easily from that data that I showed you, right? So, for example, that image. It's pretty clear from this image that these wrinkles are moving downstream at some speed. And what those plots show you is the slope of that line tells you how fast that is, what the speed is. And the fact that it's nearly a straight line means that the wrinkle here is moving downstream at nearly the same phase as the wrinkle here is moving downstream. If that plot was curved, it would mean that that speed was varying with x. So this wrinkle is moving downstream at a nearly constant speed. So that's what that's telling me. Okay. Now, here's just a few results for some other flames. So these are magnitude results. So this is one magnitude result. Here's a magnitude result for another flame. And these are just, we've taken data from flames for many years, and so I kind of have this gallery of interesting results. And so here's two pretty interesting ones. Let's start with this one over here. The result I showed you on the previous slide showed that the magnitude of wrinkling going up and then coming down. This one actually shows you that, in fact, it's going up and coming down, and then going up and coming down, and going up and coming down. So, and remember, this is not a plot of this is not time. This is magnitude of flame wrinkling as a function of space. So what that means is at each position, the flame is flapping up and down at the frequency of excitation with an amplitude given by this curve. So it means that it's flapping around a lot here. It's not flapping much at all there. Flapping a lot there, not flapping much there. It kind of looks like a standing wave is being set up on the flame. So this clearly looks like interference, and it is. I'll show you later that this is an interference phenomenon where different wrinkles on the flame are positively and negatively interfering with each other. This plot is an interesting one because we can see two length scales of wrinkling on the flame sheet. You can see this long length scale. You can basically see the whole thing going up and coming down, like I showed you in the previous slide. But you can see superposed upon it is a shorter length scale wrinkle. So that's kind of an interesting one too. And in fact, if you go back, you can kind of see it on this image. I didn't really emphasize it, but you can probably convince yourself that you can sort of see a shorter length scale modulation riding on top of that flame right there. Okay. So that's just some background, like I said, just to give you some intuition of what flames do and what they look like, both qualitatively as well as quantitatively. So qualitatively, what do we see? We see flames flapping and wrinkling. We see wrinkles convecting downstream. That's manifested in the phase. What the magnitude shows you is that the magnitude of flame wrinkling, it's not constant, that it's nearly zero at the attachment point. And that it has this non-monotonic dependence. There's locations where the flame is flapping a lot, locations where it's flapping less. And that's not as obvious from those movies that I showed you. So now what I want to do is kind of break this problem into 4 pieces, and I'm going to walk through 4 different pieces to illustrate these flame dynamics. The first thing I want to talk about is wrinkle convection. So you could see it in the phase, you could see it in the movies, but I want to talk about wrinkle convection. All right. Probably the easiest way to think about this is to give you a model problem. And I know some of you have seen this presentation because I gave it a shortened version last year at IITM. And so you're going to know the answer to this. But what I want you to think about is a model problem where I have a premixed flame that is sitting in a uniform flow velocity. So the flow velocity is everywhere UA for time less than 0. And the first question you might ask me is, this is a flame. How can the flow velocity everywhere be constant? Flames change flow velocities and they cause dilatation. And I'd say you're absolutely right. So this is an isothermal flame. So I want to illustrate flame propagation. I don't want to think about gas expansion effects right now. So at time t equals 0, I step change, and everywhere I make the velocity equal to UB. All right? So it goes from UA, and the steady state flame position is this. It's spreading, and so the angle, if you remember, the angle at which flames spread is the inverse sine of the flame speed divided by the flow velocity. And because I'm going from a lower velocity to I didn't say it, I'm going to increase UB. UB is going to be bigger than UA. What's going to happen is that the flame is going to find a new steady state where it's at a less steep angle. So the question is, what does the transient look like? You know, how does it transition? And this is a movie that shows that transient. So what you can see is that what happens is that the flame does not, steady state position for time less than 0, steady state position for time much greater than 0. The transient doesn't look like that. Rather, what happens is that at the flame holder, at time t equals 0, there's a change in the angle of the flame from its initial value to its new value, and then that change in flame angle convects downstream, right? And so the flame will reach its new steady state position once this whole piece has been washed out. So if we say, well, what happens, how do flames respond to disturbances? When you disturb the velocity of the flow, what does the flame do? Well, what you do is you generate a wave at an attachment point where the flame isn't moving. So, and what that wave is it's a change in flame angle, right, where the angle is equal to the inverse sine of the flame speed divided by the flow velocity. And then that change in flame angle just moves downstream at some flow velocity. So I'm just going to jump over this slide. Actually, let me tell you let's talk about what that flow velocity is. What is the speed with which that wrinkle is moving along the flame? It turns out it's not the mean flow velocity. That you can do a vector construction. So here's a flame. If the mean flow is doing this, here's the vector of the mean flow. But remember, the flame is also propagating. The flame is propagating normal to itself at SL. So if I take the vector superposition of U0 with SL projected along the flame, the wrinkle on the flame is going to be propagating at this speed of UT. All right? Or oftentimes, like when I showed you plots of the phase of the flame wrinkle as a function of x, if I project UT onto the x direction, so if I just take the x component of UT, like I've done here, I can define a velocity UCF, which is UC being the convection velocity, the F being of the flame wrinkle. All right? So the main point, as you can see from this picture, if I take that projection, UCF is going to be less than U0. So the speed with which a wrinkle is moving along the flame is not the mean flow velocity. In the limit, as the flame becomes vertical, very, very steep, those two become close to each other, but they're not the same. And let me just make a point here. This is data where I'm plotting velocity as a function of axial location. The reference mean velocity is given by 1, so I've normalized velocity by 1. These lines here, this is the convection speed of the flame wrinkle. All right? And the way this is from some data from our group. The way I extracted this is, if you remember, I said the phase, the angle of the slope of the phase as a function of x. That's physically equivalent to a convection speed. So that's this value. And there's two lines because I calculated the left and the right flame branch just to double check. And just for fun, what I've also overlaid on top of this is these solid lines is from PIV data. I've measured the velocity field. There's a convecting vortex, and by taking the phase of the velocity as a function of downstream distance, and again, I can take the slope of that phase, and I can get a velocity. This is the phase speed of the vortex. So what you can see here is that clearly the convection speed of the flame wrinkle is not equal to the mean flow velocity, which is not equal to the disturbance velocity. So with flames, we have this interesting property whereby we have these sources of disturbances. We have these vortices, which, as we talked about in the last part, are moving at some velocity which is related to the mean flow velocity. The convection speed of the flame wrinkle is also moving at a speed proportional to the flow velocity, but the proportionality constant is not the same. And so the source of excitation of the flame wrinkle is different, is moving at a different speed than the flame wrinkle itself. Okay, I'm just going to jump over this slide. So that's how wrinkles are convected along flames. Now let me talk about how wrinkles are excited on flames. So what I want to do in order to illustrate this is I want to go back to that equation that I wrote for the space-time dynamics of the flame position. Okay, and by the way, I've kind of pulled together a couple presentations. So some cases I'm going to call the flame position L, and other cases I'll call it zeta. So don't be too confused by it. So that equation for the space-time dynamics of the flame position, it's a nonlinear partial differential equation. There's not a general, you can't write a general solution for it. However, if you linearize it, so if you assume that the magnitude of the velocity fluctuations are small enough with respect to the mean, such that the flame wrinkles that you excite are also small. In that case, if you can linearize that flame dynamics equation, you can write an exact general solution for the flame wrinkling, which is what I've done here. And it turns out that it's a little bit more physically intuitive. Rather than looking at the flame position itself, I'm looking at the slope of the flame position, so dl prime by dx. So this is a general solution for the wrinkle dynamics of a premixed flame. And I have one thing I want to point out, since this is this partial differential equation, it's first order in space, first order in time. I need to give it some boundary conditions. And so the boundary condition that I give it is that the flame is not moving at the attachment point. I'm going to assume that L prime is 0 at x equals 0, which the data seems, and that's supported, and the reason for that boundary condition is that's what the data seems to indicate. All right, and so what you can see here is that, well, you have terms in blue, which are UN prime terms. UN prime denotes, let's see if I labeled it here, the velocity fluctuation normal to the mean flame, okay? And so this is the source of wrinkling. What's creating wrinkles? Velocity fluctuations normal to the flame. Those are pushing the flame around. And then UT bar, that is the speed with which wrinkles are convected along the flame. Those are what are convecting these wrinkles along. So for example, and in both, well, let's look at this term right here. You can see that can I turn the gain down just a smidge? Actually, maybe if I move this thing down a little bit, that'll be okay. So you can see that the flame wrinkling excited by the velocity, this is the velocity fluctuation at x equals 0, and then you have this t minus x on ut term. This is a traveling wave. It's describing physically a traveling wave which is moving at a speed of ut. All right? So this is just, again, quantifying this point that I made earlier about how flame wrinkles are convecting downstream at the speed of ut. And then we also have this other term. This is a convolution integral, which is proportional to the spatial derivative of the velocity fluctuations. And you can see this convolution operator here. Okay, well, let's start by looking at it. Let's assume that we have a spatially uniform disturbance field. So I'm just going to have a bulk slug pushing the flame back and forth. Okay, so this might simulate a low frequency acoustic disturbance. Well, in that case, this whole term goes away, and I'm left with this term right here. And so what that says is that the flame wrinkling, the slope of the flame wrinkling equals the fluctuating velocity at x equals 0, t minus x on ut. So what's happening here is that this bulk velocity disturbance, I have a boundary condition that the flame is not moving at the attachment point. So I'm zooming in on the flame attachment point. So this is maybe my hardware, my metal that the flame is attached to. Here's the flame. Theta is this angle, and as the velocity is oscillating, coming out of this burner, the flame angle is oscillating. Okay? And what happens is that, as like we showed earlier, that whenever you have a change in flame angle, it's convected downstream. So what it's saying is that the flame angle oscillates like this, but then it's also convected. That's what that is showing you right there. In fact, so here's a movie. I'm not sure you can see this in the back. I don't know if can you see that? Is it too light? It's okay. This is a harmonically excited Bunsen flame. So this ring right here is a ring of premixed flames to anchor this flame so it doesn't blow off when I'm exciting, and I'm pulsing it up and down. You can see the flame angle oscillating here, and then if you kind of try to take a Lagrangian view with your eye, you can see that flame angle whatever that change in flame angle, it's moving, or if it's here and then it's moving along downstream. So you're generating a wave at the attachment point, and it's convecting downstream. Now, a point I want to emphasize here is that, again, you have to supply a boundary condition to solve this problem. This term right here is completely determined by that boundary condition. I set L prime equal to 0 for this solution of the wave of the G-equation. I said the flame's not moving, and that gives me, this is basically the particular solution of the, the homogeneous solution of the equation. If I had said the flame position is going to move with the flow, so L prime is equal to or dL prime by dt is equal to U prime, that term would be 0. I wouldn't be exciting a wrinkle. Okay, so that term is completely due to the boundary condition. So one of the things that's interesting about this thing is that what this shows is that if the excitation velocity is spatially uniform, the entire space-time distribution of the flame wrinkling is completely controlled by flame anchoring. All right? So a point that I want to make sure people understand here is that flame anchoring obviously has a big important effect on where the flame is at the base of the flame. But it also controls the entire space-time history of how flames respond to harmonic disturbances. Flame wrinkling really matters. If I had a flame that was not anchored so well, and the whole flame was bouncing around rather than being locked down, I could get, if I were to compare that to a situation where maybe I was piloting the flame and it was anchored very strongly, I could get a completely different flame response. So one other point I want to make is that you might ask, as we've talked about, where is kinetics, where is diffusion showing up? That kinetic and diffusive effects, heat loss effects, although they're not explicitly shown, they're implicitly showing up because of that boundary condition. I implicitly made some assumptions about this stuff by assuming that L prime was 0. If the flame was maybe very weak or was about to extinguish and it wanted to lift off, then I would have a different boundary condition. So it's implicitly showing up in the boundary condition. Okay, I'm just going to jump over these. Okay, one other thing that I want to show you here is that if I, while we're talking about this behavior, let's just go back to some data. This red plot is data that I showed you earlier. That's the magnitude of the flame wrinkling as a function of downstream distance. And what I'm showing you here is two other plots as well at different amplitudes. So this is lowest amplitude, medium, and high amplitude of excitation. And as you would expect, as I increase the magnitude of flame wrinkling, of velocity fluctuations, at a given spatial location, the amplitude of flame wrinkling is going up as I increase the magnitude of the velocity fluctuations which are creating that wrinkling. No surprise there. And again, you can see all these curves heading, here I have drawn it to 0. So if you extrapolate, I don't have the data near 0, but if you extrapolate these curves back, you can see they're all heading towards 0. That L prime is pretty close to 0 at the attachment point. Now, what's illustrative, though, is to take the same data and let me normalize it by the magnitude of the velocity fluctuations which are exciting the flame. And that's what I'm showing you here. L prime divided by U prime. Okay? And you can see two things. That from, say, 0 to 1.5, the curves all collapse on top of each other. And for x greater than 1.5, they don't. Right? And in fact, I've actually added even an additional amplitude, is if you see here, the lowest amplitude, the lowest here is the highest here is the lowest there. So the fact that all these plots collapse on top of each other for small x, what does that mean? Linear, right? It means that the flame wrinkling is linear in amplitude. In fact, I think that's what that says. The near field dynamics are linear in amplitude. That means if I double the amplitude of velocity fluctuations, I double the amplitude of flame wrinkling. And so therefore, if I normalize by velocity, I get a constant value. That's what that's showing you here. Okay, the fact that these curves spread out after 1.5, that says it's nonlinear, right? So if I normalize by amplitude of excitation, I get a different answer. It's not linear. And the fact that the smallest amplitude has the highest normalized response, the highest amplitude has the smallest normalized response, what is that telling me about that nonlinearity? Yeah, it's a saturating type of nonlinearity, right? So if I double the amplitude of excitation, I'm getting less than double the amplitude of flame wrinkling. That's what this is showing me. So, and this, we talked about, I mentioned this before when we showed you the data that this came from, how it looked like it was saturating, right? I showed you data at 10 times, at 0.01 and 0.1, and I had made the comment that the amplitude of excitation is not 10 times bigger in this image. And that's being quantified on this plot. Okay, so that's all I want to, so that's, I've talked about how wrinkles are convected along. I've talked about how they're excited. Now I want to talk a little bit about interference effects. Yeah. Yep. Yeah, I'm going to talk about that. We'll get to that. Flame propagation imposes a certain kind of nonlinearity, which gives you that saturation behavior. Yep.
Does the wrinkling, flame wrinkling frequency, I mean the frequency of this wrinkling, depend on the flame position? Is not equal to the forcing frequency, yes?
Yes.
Because of the nonlinearity.
Say it one more time.
Because of the nonlinearity?
No, that's not a nonlinearity. I mean, a linear system, the response frequency is equal to the input frequency. So what we're doing is the forcing is trying to simulate the effect of a flame inside of a combustor with a certain natural mode, and you have these narrowband oscillations which are forcing the flame. Yeah. That's right.
So in which case, if I take a wavelength of flame front, which is oscillating right now, and convert it to area function.
Yep.
Will I have twice the frequency of oscillation area?
Say it one more time. Why is the frequency of oscillation?
Because the area is a scalar or heat release is a scalar.
Yep.
So the pi by 2 phase of the time will be this, and the 3 pi by 2 will be this.
Yep.
Both the area has to be the same.
You're saying that even if the flame is wrinkling, that the area would not oscillate in time?
Will it oscillate at twice the frequency?
Okay, so the area is a nonlinear operator, right? So you have, this is a good question. So if this is L, well, let me do it the other way. You can define the flame position with either coordinate. A differential element of surface area, as I think this is what you're saying. Is that? So for a differential element dx, the differential surface is this. And so this total surface area is the integral from x equals 0 to L of that. So there is a contribution. The flame area is oscillating at the forcing frequency, but there's also, as you're pointing out, an oscillation at harmonics, because this is intrinsically nonlinear. No, it won't. Because when you linearize this thing, what you get is the only time it would not oscillate is if dl naught by dx equals 0. You would only get oscillations at 2 times the frequency. Otherwise, you have if dl naught by dx is non-zero, so you have square root of 1 plus dl naught plus L naught plus L1 by dx squared. When you linearize this thing, it's going to look like this. It's going to have a term dl1 by dx linear times, some stuff, like 1 plus, I can't remember what it looks like, dl naught by dx squared or something like that. So yeah, it's a very good question, but I can tell you that there is a contribution at the forcing frequency if the flame has an angle to it. Only if the flame is perfectly flat to the flow would the contribution only be nonlinearity. Only nonlinear. There would be no linear response term. The linear term would be 0. Only in the case where the flame is flat. Once it's at an angle, you have a linear term. Sure. Yep. Okay. All right, so what I want to talk about now is, so I just gave you a very simple problem where the disturbance field was spatially uniform. What about if it's varying spatially, right? This is the interesting problem, like a vortex. I've shown you all these images where you have these convecting vortex trains. It's pretty obvious that the velocity field has some strong spatial variation. And in fact, it's varying spatially over a convective wavelength. Well, that means that this term is not going to be 0, right? And now life gets pretty interesting, because what's happening is this is a convolution integral. So let's think about what this equation is saying. It's saying that the flame wrinkle, particularly the slope of the flame wrinkle, it's equal to, at a position x, is equal to the integral from 0 to x. All right? So it's a convolution integral. So in other words, the flame wrinkling at a position x isn't just a function of the velocity field at x. It's an integral of the velocity field from 0 to x. Okay? So, and specifically what that convolution integral is saying is, if we go back to this picture, suppose I only care about, I just want to calculate what the flame is doing right here. Okay? Well, what this is telling me is I can't just look at what the velocity field is doing at this position x. I have to look at what the velocity field was doing at every upstream point. And specifically, you can see this convection term. And what this convection term is saying is, okay, you want to know what the flame is doing here? You're going to need to know what the velocity field was doing here at an earlier time. All right, so if I want to know what the flame is doing at this position x at time t, I'm going to need to know what the velocity was doing at an earlier x at an earlier time. What earlier time? The time t minus, well, x minus whatever this is. I'll just call this x prime. T minus x over x prime over ut. Plus, so in other words, I have to take the velocity disturbance at every upstream point with a suitable time delay, and the time delay being the time delay required for the wrinkle excited to convect to this point. And so what this is showing you is that the flame disturbance at location X, it's a convolution of the disturbance at every upstream point at earlier times. The flame has memory. Okay, the flame has memory. It's not a local operator. And that's what makes this problem really interesting. The flame is not a local operator. It's not just responding to the local disturbance field. It's responding to the entire space-time history, well, the entire spatial history with an appropriate time shift of what was happening upstream. And I think this point is really interesting because I think it's not well appreciated in the turbulent combustion literature. Because if you think about it, what's a standard turbulence closure? Well, a standard turbulent closure for say, turbulent flame speed. You know, like an LES subgrid closure might be ST as some function of the turbulence intensity at that location, right? At that location. And so implicitly, a lot of these turbulent flame speed closures, they're really, they're neglecting this memory effect. Well, if the velocity field is spatially homogeneous so that the U prime characteristics at every upstream point is the same, then that effect is a wash. But if you have a stratified flow where the turbulence intensity is spatially varying along the flame, that could potentially be an important effect. Anyway, I just wanted to, that's a little bit of a tangent, but just main thing is premixed flames, actually non-premixed flames as well, they both are non-local. And it's due to the fact, it's due to the convection term, that wrinkles are convecting downstream. And so if you want to know the flame wrinkle at this location right here, the flame wrinkle at this location is the superposition of flame wrinkles excited at every upstream point with a suitable time delay to give you whatever you have there. Okay, well that's one point I wanted to make about that. The other point is that if we think about this, this is telling me, this right here is sort of the flame response. It says that if I create a wrinkle on the flame, that wrinkle is going to convect at this speed of U, what I've called UT, the wrinkle convection speed on the flame. But the velocity fluctuation itself has its own space-time dependence, right? The interesting velocity fields are, you know, like you have a convecting vortex, which is disturbing the flame. So what's happening is you have this vortex, which is inducing a velocity fluctuation normal to the flame, which creates a wrinkle, and that wrinkle starts convecting downstream. Well, that same vortex is also convecting downstream, and it's continuously exciting wrinkles on the flame as it's convecting downstream. But those wrinkles are also moving downstream. And as we talked about, actually I showed you this data earlier, the speed with which the wrinkle on the flame is moving is not the same speed with which the vortex is moving. So this vortex is moving along the flame, it's creating wrinkles, but those wrinkles that are excited are moving at different speeds. So what's going to be the overall impact of that? Well, in order to see the overall impact, let's just take a look at a very simple model problem. All right? Let's assume that my velocity disturbance field looks like this. So the fluctuating velocity normalized by the mean tangential velocity, there's a slight change in nomenclature. This is that UT. With an amplitude of epsilon, and it's a traveling wave. So I'm going to assume that I have a velocity fluctuation that never decays, that it's moving actually at a speed of UCV. UCV is that vortex convection speed. Let me take that expression for velocity fluctuation, plug it into here, and solve for the flame position, okay? Which is what I've done here. Okay, and like I said, I'm kind of going back and forth between two nomenclatures. Zeta is the same as L, it's the fluctuating flame position. And this is what you get. And there's some details here. The main thing I want you to see here is that it's the complex exponential. They both go as e to the 2 pi I ft. So this term and this term are both oscillating harmonically at the frequency of this convecting vortex. Then you have this term with a spatial dependence, which is moving, which has a phase speed of UCV. This is the particular solution. You have this term, which is moving at a phase speed of UT. And you have the difference between these two complex terms. It's a little bit easier to just graph it, which I've done on the next page. So what I'm plotting here is the magnitude of flame wrinkling, all right? So there's a magnitude and phase of flame wrinkling as a function of downstream distance. And notice how you get this interference pattern. Okay, so this is magnitude of flame wrinkling. It starts at 0. It starts at 0 because it has to, because I told it to, because that's the boundary condition. The magnitude of flame wrinkling grows, reaches a peak, and it actually goes to 0. Then it grows. And actually, if you were to plot this, it would just go on forever, infinitely. And the reason it goes on forever is because I assume that the vortex goes on forever. It didn't decay. In reality, you wouldn't ever get this because the vortex is decaying. But you can clearly see this interference pattern, and in fact, what you get is a new length scale in this problem. So we've talked about length scales associated with acoustic disturbances, with vortical disturbances. You actually get a length scale associated with this interference pattern, and here's a formula for that length scale. Lambda, this interference length scale, lambda int, this is that convective wavelength, and you can see it's proportional to 1 over the absolute value of the ratio of the flame wrinkle convection speed to the vortex convection speed minus 1. So if this ratio is 1, in other words, if the vortex is moving at the exact same speed as the flame wrinkle, what would be the interference wavelength? Infinite, right? Which is another way of saying there's no interference, right? You don't get interference. And because the two disturbances are moving at the same speed, as soon as this moves away from a value of 1, you start creating these interference patterns. And you can also see that the closer these two are, the closer this ratio is to 1, the bigger that interference length scale is. The farther they are from 1, the shorter they will be. So, so the limit might be, for example, if you had a bulk disturbance, if you had if the disturbance was bulk so that UCV was infinite, this would just become 1 over magnitude of 0 minus 1, and the interference wavelength would become the convective wavelength. So what this is showing you is that this interference wavelength is directly proportional to how different these two phase speeds are. So I talked about, when we talked about the superposition of an acoustic disturbance and a vortical disturbance, we also saw interference patterns in the velocity. And I talked about how when you have two disturbances moving in the same direction at different speeds, you set up an interference pattern. The same thing is happening here. In this case, we have two sources of wrinkles moving along the flame. One is the vortex, which is continuously exciting wrinkles, and then the flame, which is propagating those wrinkles. And those are adding up in and out of phase with each other, and you're getting spots where you're getting big wrinkling and little wrinkling. And so if we think back to the data that I showed you earlier, this was one data set that I showed you. It's pretty obvious now what's happening with this data. You're clearly seeing an interference pattern. In this, the interference pattern is dying away because of nonlinear effects, which we'll talk about next, and the vortex is decaying. But you're clearly seeing that interference pattern. Here, what you're looking at, this one's really a fun one because what you're looking at is you see a long length scale interference pattern, and superposed upon it is a shorter length scale interference pattern. And what you're seeing there is one of these is due to the vortical disturbance, and one is due to the acoustic disturbance. So the flame is filtering the long wavelength acoustic disturbance differently than it is the shorter length scale vortical disturbance. Okay. And again, let me just make one more point here, that if we had a randomly oscillating convecting disturbance, if you solve the same G-equation, but you excited it by a stochastic disturbance where you don't have that space-time coherence, here's a plot of what you would get. This is the RMS magnitude of flame wrinkling as a function of downstream distance. If you excite it with a single frequency excitation, you get these interference patterns. It starts at 0 because we tell it to, and then it oscillates. If you excite it with the same RMS amplitude, but without that space-time coherence, you get this. All right? So this should look familiar to you, because what you're looking at here is basically what this is showing you is that the turbulent flame brush, you can think of this as being the turbulent flame brush, the width of the turbulent flame brush growing monotonically with downstream distance. So this goes back to a point I made earlier, is that the ways in which flames respond to space-time coherent disturbances and stochastic disturbances is totally different. It can be the same value of U prime, the same U prime RMS, but the space-time coherence of those disturbances give you completely different behavior. Okay, the last thing I want to talk about with premixed flames is destruction of flame wrinkles. All right? So it turns out that when you linearize the G-equation, you lose an important piece of physics, which is that premixed flames don't like to be wrinkled. They like to be smooth. All right? So the very action of flame propagation, if you take a surface and you propagate it normal to itself, that will always act to smooth a wrinkle out. All right? So as I've shown here with this picture, so imagine that I take a flame and I just wrinkle it, and then I say, okay, what happens next? It's going to propagate normal to itself, and these two parts are going to collapse on top of each other. If I just draw a picture, if I take a flame and I add some arbitrary wrinkle, and I say, okay, what happens next? It's going to propagate normal to itself. And for example, you can see this pocket is going to go away because these two branches are going to pop into each other. And so given some later time instant, the flame is going to, it's going to be much, much smoother. And if I completely remove the disturbance field, if I started like this, the flame would become flat after some amount of time. So Norbert Peters calls this property, and he came up with a word which I like, and he calls it kinematic restoration. So kinematic restoration is the restoration of the fact that premixed flames want to smooth themselves out because of the action of flame propagation normal to itself. And in fact, this movie that I showed you earlier from Professor Kandel, you can see kinematic restoration very nicely in action. So if you think about the picture that I just showed you was in time, imagine taking that same pattern and propagating as you're going from this to this. Imagine that the whole thing is convecting at the same time. That's exactly what we're seeing here. You can see this harmonic wrinkle, and then if you watch the part that's concave to the reactants, you can see two branches propagating into each other and destroying each other. Whereas if you look at the part that's convex, you can see how the wavelength is getting longer and it's smoothing itself out. Yep.
So thinking is a self-excited dynamics because whenever the pinches out, suddenly the flame is going away.
You mean like right there? Yeah. So what's happening there is the again, this is kinematic restoration. So I'll try to draw what the flame did there. This is this is products. This is reactants. Remember, these two flames are propagating into each other, and they just consume all the reactants in between them. And so at the next time instant, this flame is going to look like that. So it's not extinguishing. It's just the two branches have propagated into each other, and they've consumed all the reactants in between. So when this happens, you can get very, very big changes in heat release in a very small amount of time. You can get big puffs of. This is oftentimes when flames will make a lot of sound too. Is when you get these types of behavior and you get really rapid destruction of flame surface area. So the way this oftentimes manifests itself in flames is you get, as you increase the amplitude of excitation, you get vortex roll-up. Can you guys see this picture over here? So if the flame was a passive scalar, or if it was being disturbed by a really strong amplitude disturbance, the whole front is getting wrinkled like this, but now you just propagate this thing normal to itself, and you can see that at some later time instant, it's going to look like that. And you can see that these movies that I showed you earlier. You can clearly see kinematic restoration going on. So you can see the whole flame getting rolled up here, but then as you move downstream, you'll see it going away due to propagation normal to itself. Okay, well this process is amplitude dependent. It's nonlinear. So somebody asked me earlier, where is the saturation coming from? This is where it's coming from. You take a flame and you perturb it with a convecting vortex. If you double the amplitude of the fluctuation amplitude, the flame just doesn't wrinkle twice as much because it turns out that the rate of kinematic restoration increases nonlinearly faster than the amplitude of excitation. And let me just show you, I'll just show you a, oh, actually, here's one more simulation just showing this kinematic restoration effect. Here's a harmonically oscillating flame holder exciting these wrinkles. And so the flame is propagating normal to itself. And so you form this cusp. By the way, this is the other thing that happens is you form these discontinuities or near discontinuities in derivative in flame slope due to kinematic restoration. You can see that there. But let me just show you, so this is that data that I showed you earlier. You can clearly see that saturation behavior. Let me just show you a calculation that illustrates this as well. This shows a calculation of the magnitude of flame wrinkling as a function of downstream distance. And what I've done is I've set the vortex convection speed to nearly equal to the flow velocity, so you don't really get much interference. Okay, that's why these plots look like this. And what I've done is I've done the simulation at 3 different forcing amplitudes, and because it's linear, these amplitudes all, this shows the linearized solution of the G-equation. Okay, so if I do it at 3 forcing amplitudes, if it's a linearized solution, this will just be, this curve and that curve are identical except for a scaling factor. So this is what you get if you linearize it. Now let me turn the nonlinearity on, all right? And this is what you get for the lowest amplitude forcing. So you can see it's nearly identical to what happens at near the flame holder, but then it starts to diverge. And whereas this curve stays constant, because remember, there's no mechanism for destruction of flame wrinkles if you linearize the G-equation. But when you turn on the nonlinearity, that flame wrinkle starts to go away. If I turn up, for the higher amplitude of excitation, you can see the curves diverge sooner, and this curve drops faster. At the higher amplitude of excitation, it drops even faster. And so you can see the same type of behavior. And so what's happening is that this kinematic restoration effect, it takes time. Right? The flame is propagating normal to itself, which is why the flame is actually quite linear near the flame holder. But this effect, as it accumulates, its effect starts to grow with downstream distance. It's very, very similar to gas dynamics if you're familiar with shock formation. If you take a disturbance and you let a disturbance propagate in a tube, you get wave steepening, and eventually a pressure disturbance becomes a shock. But that takes time. It takes time for those nonlinearities to accumulate. It's the same, it's a different, the specific nonlinearity is different, but it's the same basic effect. And so you get that. In fact, if I take that same data and I go back to the absolute form, you can kind of see some similarities. You can see how, you can see this red curve is dropping faster than the purple curve in absolute units, which is what you can see here with that solution. Okay, I'm just going to jump past. I have some other physics which I don't have time to get into, but I think that summarizes the key physics that I wanted to leave you with premixed flame dynamics. Is that wrinkles convect, and because of the action of convection of flame wrinkles, flames are non-local, and because that the sources of flame excitation, like vortices, are moving at different speeds than the flame wrinkles, you get interference effects. That was another point I made. And then the last point was that kinematic restoration, the fact that flames propagate normal to themselves, makes premixed flame propagation intrinsically non-linear, okay? And that non-linearity causes wrinkles to be destroyed. Okay, let me I got 5 minutes. Let me just quickly leave you with a couple thoughts on non-premixed flame dynamics. And so what I'll do here is, let me just show you some results for this flame geometry. So remember, non-premixed flames are described by the Z-equation, the mixture fraction equation. And the left-hand side was the same as premixed flames. You have a convection operator. And as you might expect, just as premixed flames convect wrinkles, non-premixed flames also convect wrinkles. And for the same reason as premixed flames are non-local and will give you interference effects, in the same way, non-premixed flames are non-local and they give you interference effects. The key difference of premixed and non-premixed flames shows up in terms of the term on the right-hand side. The premixed flame has this normal propagation operator, which gives you the nonlinearity. Non-premixed flames have a diffusion operator, right, which is quasi-linear. But it turns out that diffusion operator, just premixed flames propagate normal to themselves and get rid of wrinkles. Diffusion also doesn't like gradients. So that diffusion operator also smooths out wrinkles, but for a different reason. One is nonlinear, though. The other is linear. The non-premixed flame problem is actually linear, or quasi-linear. And let me just show you a couple quick results just to illustrate this. Let's look at basically a Burke-Schumann flame. Let's suppose I have a fuel jet, an oxidizer jet. The flame is going to be sitting at the Z-Stokes surface, the point where the fuel and oxidizer are at their stoichiometric ratio. And I'll use the same variable, or zeta, or I've called it L, which is a function of x and t as denoting the instantaneous flame position. And what I want to show you on the next slide is, suppose I have bulk forcing. Suppose I'm just oscillating the flow in this direction. What happens? Well, here's math. Here's what the solution looks like. But if you actually plot it, here's a movie of the Z field. So red is pure fuel, blue is pure air. You can see the whole Z field is oscillating in time. What I'm particularly interested, though, is the value where Z is equal to Z Stoke. Where did it go? There it is. So this would be an instantaneous snapshot of the Z field. I'm particularly interested in this iso contour where Z is equal to Z Stoke, because that's telling me where the flame is. All right? And again, you can see these wrinkles on the flame. They're convecting downstream. You could, although I didn't overlay it, let me see if I overlay it. No, I don't. Okay. You can, just from this right here, you can see that these wrinkles are convecting downstream. I'm basically out of time, so I think I'll stop here. But as I mentioned earlier, the space-time dynamics of the non-premixed flame and the premixed flame, they both have a lot of similarities. They both convect downstream. As I said, you get interference effects if the vortex or whatever it is that's exciting wrinkles is moving. And also, the premixed flame doesn't like wrinkles because of flame propagation. The non-premixed flame doesn't like wrinkles because of diffusion. One causes wrinkles to decay in a nonlinear amplitude-dependent fashion. The non-premixed flame, it's a linear effect, which causes the wrinkles to go away. Does anyone have any questions?
This is gaseous propellants are used.
Yeah, purely gaseous. Everything I've talked about here is gaseous. That's right. There is no good general theory for non-premixed flame dynamics for spray. What was that?
Gaseous also without flaring. Flare velocity is not there.
Yeah, but you can, the same points that I've made, if you have swirl, doesn't change what I've just said. It just adds a third dimension to the problem. And in fact, there are solutions for swirl velocity fields for gaseous. By the way, let me just, one more thing. I've talked here about the space-time dynamics of the flame position. I didn't have time to talk about the heat release fluctuations. And there are some similarities, but there's also some significant differences, all right? So I'll just point that out. So in the book that you have in your bag, chapter 11 of that text is on local space-time dynamics. Chapter 12 is on heat release dynamics, and it talks about some of those differences. Yes, sir?
All these are related only to 1D, one-dimensional harmonic excitation.
1D, what was that?
Is all these are related to 1D harmonic excitation? When we excite harmonically in only one dimension, in the x-coordinate, all the analyses are related to that.
So you mean spatially 1D?
Yes, spatially.
So the model problem that I showed you, just to keep things simple, it was a 1D excitation. But the general physics that I just kind of qualitatively expounded is true for an arbitrary multi-dimensional velocity field.
It can be extended to 2D even.
Oh,
2D
absolutely.
harmonic
Or
excitation.
3D. Yep. Yeah, so in fact, we've worked problems, for example, an example of a 3D velocity field would be a convecting helical vortical disturbance. And we've solved this problem for that case as well. But the same deal happens. What happens, though, when you add swirl, the question about swirl, is what that does is axial flow velocity convex wrinkles in the axial direction. Swirl convex wrinkles in the azimuthal direction. Well, if you have an axisymmetric disturbance field, the swirl effect is kind of irrelevant, because if you have an axisymmetric disturbance spinning it around, it's still axisymmetric. If, however, you excite the flame with a helical disturbance, so you have an azimuthally varying wrinkle field. That whole wrinkle field is convecting and spinning, and so you get interference patterns not only in the axial direction but also in the azimuthal direction. It's a really interesting problem.
Thank you.
So is there a
Yes.
diffusion flame equivalent to the kinematic restoration?
To the what?
The kinematic restoration, the non-premixed.
Not really. But again, diffusion flames are trying to smooth gradients out, right? So that diffusion operator, so this is the Z field. Diffusion doesn't like gradients, right? So it's trying to smooth these things out. And so it is causing these wrinkles to go away, but not through the action of kinematic restoration, but through the action of diffusion.
But this is much weaker than the.
I wouldn't call it weaker. I would just say that it's different physics. The one is propagation of a surface normal to itself. The other is trying to smooth out gradients.
This would be a slower process.
Pardon?
This would be a slower process.
No, not necessarily. Not necessarily. But the one effect is not intrinsically nonlinear. The other effect is linear. So that's a fundamental difference between the two. Which means that, I showed you how the premixed flame had this significant saturating character due to the kinematic restoration. That you don't have that for the non-premixed flame. That the wrinkle destruction process scales linearly with amplitude rather than nonlinearly. Yes?
In case of hydrodynamic stability, the nature of the stability changes from two-dimensional to three-dimensional flow. Can't generally extend, suppose a flow which is stable in a two-dimensional way, say channel flow is not, it will be stable for hydrodynamically, and if you take it in a pipe flow which is three-dimensional,
Yep.
the characteristics changes.
Okay.
So,
Okay.
can such a phenomena is observed in these cases?
Okay.
Simply explain the runtime.
I'm almost done. So I'll answer that question, then we'll be done. So just remember, there's two things going on here. Let's just. Where'd it go? Well, let's just look at this one. This is the G-equation, but the same effect would apply for the non-premixed equation. This is an equation that tells you what flames do to a given velocity field, right? That is the flame dynamics problem. What is the velocity field that's exciting the flame? That's the hydrodynamic stability problem. So the flame dynamics is a much simpler problem, and there's basically convection on the left side, convection of wrinkles by the mean velocity field and creation of wrinkles by the normal velocity field. So whether it's 2D, whether it's 3D, there's no new physics there. It's just all buried in the convection operator. The right-hand side is destruction of wrinkles by kinematic restoration. So the hydrodynamic stability problem is a much, much more complex problem, and where that feeds into this is controlling the space-time dynamics of the disturbances that are exciting the flame. And what makes life even more interesting is that those couple because of expansion across the plane. All right. Thank you all very much.